It's lowercase. Yes. It's not a constructor. It's a keyword. Yes. Okay. But you see that we're not using this 0. We're not using that REFL. If we pass them in as arguments, we would not be using them, right? So here, like fin in, oh gosh. What's the type of suck? Right, so if we have something that's type fin m, we have an m, that's a nat, and we have a fin m, and we do suck of lambda m x, and we do suck x. What do we fill in here and here? And what do we get as a result? Huh? Suck m here. And then what should we put here and here? Probably that's REFL. And we want that m maybe? Right? Does that work? We can always ask the type checker. Yeah. But notice that we can make this m implicit, right? Why can we make this one implicit? Because it's only used in square brackets, right? Because it only gets used there, right? So the fact that we've marked these elements of this data structure as implicit means that we can use that in our analysis of use. Incorporating in the data structure doesn't really count as a use because we're just going to erase it anyway. So that's great because we make our code fast. But there's also a little bit of a drawback in that we have to think a little bit. We don't have the automatic analysis that Idris does. We actually have to think about, are we going to really want to use this later? When we stick some values in a data structure, we have to know, are we ever going to need it? Because we have to choose the right data structure that is going to keep it around or is not going to keep it around. So this means that when you think about products, there's actually lots of different kinds of products, right?
Do you think you could have another version of fin?
Huh?
Do you think you could have another version of fin without square brackets?
Yeah, so here's the version without square brackets.
You could do more things with this guy.
Yeah, you could do more things with this guy.
What can we do with this guy?
Actually, this guy's a bad example for something that David brought up, right? So this guy's a bad example because even when you leave it out, you can kind of get it back, right? So that's true for fin, right? Or is it not true? Am I making this up?
I think you can still write a term that will operationally
Yeah.
use the nat as an constructor. But logically, if I don't use anything,
Well, like this 2nat, this nat that you get back, right? So, yeah. So that takes a fin n and gives you the number it corresponds to, right? Yeah. So we could have also have written another way. We could have written 2nat. We could have written it like this, right? That would be a lot easier. But this version of 2nat works even if we had made this implicit and these guys implicit, because it's not the same 2nat. Oh, no, you're right. That's not the same 2nat. Case F, this one. No, this is not the same 2nat. No, I'm like completely telling lies. Yeah. Can you get it back? No, you cannot get, no, you can't get it back. Yeah, okay. If you had a singleton type, though, you could get it back.
What are we getting back?
Let's go back to this one here. This guy. Of, let's say, n equals 0. So this is not fin. This is a singleton type, right? Where the index, it's not very useful in pi, right? But it's the type index tells you what the value is. And some components we made it erasable, but we know what those components are going to be. Right? And I think when you get to vectors, the length of the vector is built into the vector itself. You might be able to recover the length even if you've erased it. Let's look at, so let me go back to product for a little bit, because I kind of want to make the point that once you start marking parts of the data structure as erasable, you have to make choices, right? And when you have products, a product is just two things together that may have some dependency between them, right? But there's a lot of different kinds of products, right? We can have a product where both components are around at runtime. We can have a product where only the second thing is around at runtime, and the first thing is erased. And notice that for this product, this dependent product, since they're both around at runtime, we can define both projections. You can take the product, decompose it, get either the first component or the second component, right? Project 1, project 2. But when we have the product where the first component is erased, then you can't project out that first component, because that would be a use of that component. So if you look here, this eproj1, I have it commented out because it's not going to be type checking. It doesn't type check, right? We project out of products by doing this case analysis. We pattern match, we get the two components, and then we return the first one. But that could be considered a use of a component of a data structure that we've marked as erasable. And so this, if we try to run this, here I can show you. If we try to run this file, and we try to project out that erased component of that data structure, then we get a type error message that says you tried to use an erased variable. And so that's two products. But of course there are more, right? Because we could also have a product where the first one is around and the second one is erased. Right? So this one. And so I've given them names because often you think of products where the first component is erased but the second one is around. That's a lot like an existential type. Right? So in Haskell has these data structures that have existential components. They're a type component, and then the second part of it depends on that type component. So this is the closest analog to an existential type in this language. Yeah?
Why is the use of X in the type of eproj2?
Oh, yes. How do we write eproj2 when we can't use eproj1? Right. So in this version, look here. So look at the type of proj2 when both components are relevant. Right? This is a very strong type for the projection. Right? It says that because the type of the second component can depend on the first component, we actually have to project out the first component in its type, right? But for exists, we can't actually project, we can't write eproj1. So how could we write eproj2? Well, we can still inline here. This doesn't count as a use because it's just in a type. And so if we could still inline that body of eproj1. eproj1, it's just case, right? So we can't define the function, but we can use it. So maybe we're not quite as flexible as we want to be, but we can still do some operations over erasable components as long as we erase that part, as long as we erase that code.
How do we know when we got this right?
How do we know when we've got this right?
When we haven't made a mistake in erasing too much?
Yeah, this is where you have.
Apart from trying to type check it, seeing if it works.
Yeah. You have to look at, I mean, you have to go to the mathematicians and say, is this consistent? Do you have a proof of consistency? Right.
I guess the related question would be, is there a most general erasure?
Yes.
If there's always a most general, then you can always just do that one.
For any function, you can, no, because of data structures, right? Right.
I feel like it would go wrong if you could erase one or erase the other, but you couldn't erase both of them or something like that. As long as there wasn't anything like that, you could just keep erasing everything independently.
Yeah. So let me show you an example of why this is hard. Here's a function, right? Lambda f, lambda x, f applied to x. Okay? So what type can we give to G? We'll make it monomorphic for now, right? So maybe it works with Booleans, right? So maybe f is bool, arrow bool, arrow bool, arrow bool, right? Maybe it has that type, but maybe it has this type, right? And we don't know which, right? And neither one is usable in the other context, right? So if we gave it this type, we wouldn't be able to supply a function that actually uses its argument to this function. But if we gave it the other type, then it would be saying, I actually do use my argument, right? So there's no principal way of saying. Oh, or maybe we need to, maybe, like Simon says, once you have something, you have to abstract over it.
Yeah.
Add it to the language. Okay, how are we doing on time? Yeah.
Couldn't we write eproj1 if we give it an erasable return?
Could we,
We only use it.
there's no, we don't really have an erasable return type.
Oh, okay.
Yeah, we would have to think about how to, I don't know how to do that. But that would be an interesting extension to try to think about. I don't know, yeah.
Maybe I'm being naive, but it seems like
Yeah,
you can only use it in an erasable
yeah,
by changing the type.
yeah. I think the Moldal version might be a little more flexible in this way, right? Where erasability is kind of a modality instead of a type. But it's been a while since I've looked at it. Yeah.
I had a question about this. If I have an erasable thing that's
Yeah.
a structure,
Yeah.
and I want to put a piece, something that's inside that structure into another erasable position,
Yeah.
with this projection function, you know, no projection function is going to be able to return an erasable thing. Maybe I'll set this up again. I have a
Yeah.
value
Uh-huh.
that I know is erasable.
Yes.
And I want to project something out of it and put it in an erasable position.
Yes.
As a function.
Yeah. Uh-huh.
There's no projection I can write because every single projection function is going to have a non-erasable.
So you can't write a projection function, but you can always put a case statement.
Okay.
Right. You can always do a case. So what it is it,
You can
yeah,
inline.
yeah. So what it is it's unpack, right? You need to know the scope of how you're using the thing. When you take an erasable part out of a data structure, you need to bound its scope somehow,
But
right?
I guess I'm saying, in principle, it seems like you should be able to somehow say,
Yeah,
if I'm dumping in only erasable things into a function,
yeah.
only erasable things can come out, and I should be able to use that in another erasable position.
Yeah, but you don't know that you're only using that in erasable positions, right? So functions, they don't really tell you if they can be used or not. Right, and that's we don't have that flexibility in this type system, right? Maybe there's another way we could set up the type system that could track that, but we're not tracking that. And so what that means is when you take erasable things out of data structures, you have to do it in a way where the scope is bounded, right? Like in a case expression. Okay. Once you start playing around with erasability, it's kind of fun. I mean, you still have to think a little bit more about whether you're going to keep the first component or the second component, or when you go to vectors. Let me show you vectors, right? So here's a version of vectors where we've made the proof here erasable, and we've made this im erasable, right? Where the vector, it doesn't have to keep its length at runtime. The length is only a compile time part of the vector, right? But what that means is when you start, so I did this, and then I went to the vec.agda, and I started trying to copy it over to see what happened, right? And I noticed some weird things, like, so vec.agda, it defines map for vectors using the applicative functor, right? Using these two components, app, zap, and pure, right? So in like this, right? So you can define map as zap applied to replicate. You may to map over a functor or over a vector. You can make a vector of functions, and then you can apply each of those functions point-wise to the vector of arguments, right? So replicate makes a vector of functions of a certain length, and then zap applies each of those functions to all of the arguments in the argument vector. So that's one way you can define map. You can also define map using the normal recursive iteration over vectors by just taking your function and applying it to each component. But these are actually, once you're starting to track whether arguments are used at runtime, these two definitions are different from each other. And because notice that this map in and map, they have different types, right? And the reason they have different types is one of them, we need to know the length of the vector up front. So we need to know how much to replicate. Whereas the other one, we just keep on going down to the vector, through the vector until we get to the end. So things start to pop out, and you kind of have to think about it. And then when you start making folds over vectors, you have to decide the thing you're folding, does it get to runtime access to n or not? You have to think about that. So that's something to be aware of. Now, the next thing I want to talk about, so we've talked about the erasure just for making code go fast. And it's great at that. But there's another interaction with erasure independently typed languages, and that is equality. All right? And I've been kind of hinting at this through all of these lectures and showing you different variations of equality. And the important thing about ICC star is not, they weren't, actually ICC, they didn't care about making the calculus of constructions go fast. What they really wanted to know is, could we only use the relevant parts at runtime in our definition of when things are equal? What parts of the term do we really have to look at when we're deciding two terms are convertible, right? So not only do we want to erase all this type information when we're running the code. But maybe we also want to erase all this type information when we're comparing two terms for convertibility. When we, at compile time, when we're trying to decide whether they're equal to each other, whether type A is equal to type B, maybe we want to erase them first and then compare them. And that's exactly what these languages do. Why? It's a lot faster for convertibility. It makes the compiler faster, right? And under the covers, unbeknownst to you, I've been doing this all along. So if we go back to equal, right? I didn't point this out, but let's look a little more closely at this definition of equate we've been using, right? Look real closely at the lambda, right? You could think about it as erasing and then comparing for equality, or you could think about as you're traversing over the term, just ignoring the parts that would have been erased. And so if you look at lambda, so I take lambda, I have bind 1, bind 2, I unbind them, so I get the variable x and I get the two bodies of the lambda, but I completely ignore any type annotations on the lambda. I don't check to make sure that the lambdas are annotated with the same type to decide whether they're equal lambda expressions, right? And in fact, one of them could have a type annotation, one could have just left that type annotation off, and they're still going to be equal to each other, right? Is lambda x dot x equal to lambda x colon bool dot x? They're both identity functions, right? So, and then if you look through here, anywhere there's any sort of type information, right, for annotations, I ignore them completely. For if expressions that were annotated with their types to help us with their refinement. For equate, I ignore that. I don't require that those type annotations be equal to each other. See if there are other ones. Oh, and then for application, let's go and actually talk about how we implement application. So, back up a minute. In the syntax, you remember application isn't application of a term to a term, it's application to a term to an arg. And the reason it's term to an arg is because that arg notes whether it's a runtime argument or a compile time argument or an erased argument. So this epsilon, right, epsilon is just a marker. Is this something we want at runtime, or is this an argument that's erased, that should be in square brackets? And so an argument, whenever we do an application, we notate, were there square brackets here? Is this an erased argument, or is this a runtime relevant argument? And so any application has that pi is noted, pi types are marked with an epsilon to know whether they're abstracting over runtime arguments or erased arguments. Lambdas are notated to whether they are also abstracting over runtime. So all these epsilons that we were ignoring, that's what they were for. And then back at equal, when we look at arguments, when we're trying to compare arguments for equality, we have an application, and then we're looking at the arguments. In the application, are they equal? If they're both runtime arguments, we compare them. What if they're erased arguments? What if they're not relevant at runtime? Let's just ignore them. Do we care whether they're equal to each other? They're not really necessary for runtime. They're not going to change how the program runs, what answer we get in the end. So why not equate them with each other? Why not just ignore them?
Because we're trying to ask whether two types are equal. We're not trying to say we run this code up or down. We're trying to say, are these two types equal?
Are these two types equal? Yeah.
It's away and saying, oh, never mind. No, they're equal. Seems a bit cavalier.
It does seem very cavalier, doesn't it?
But you're
But-
just telling us, well, it kind of works out.
Well,
You ask a mathematician.
let's talk about what, okay, you're right. When you type check, the fundamental question is, are these types equal? Right? And when you look at list bool and list int, you better not lose the int in the bool, because you don't want list bool to be equal to list int. Right? Those we do not want to throw away. And this is going back to your question from before. Right? It would be fundamentally unsound to throw that away. Right? So in terms of forming the type, that int and that bool have to be equal to each other. Right? But what if we were trying to decide whether these two types were equal to each other? I'll just write them in our buffer. Right? T1. Right? Bool, is that equal to ID type? Ooh, I need a new. Yeah. Yeah. That's okay. That's not throwing things away. But what if we had some other thing here? What about if we had ID one expression that eventually produced type and another expression that eventually produced type? Are these equal to each other? They're going to normalize to the same thing.
How do you know they're going to normalize to the same thing? In this particular case,
Yeah.
goes up.
Hmm.
But if it was, let's say it was constant function, so it had an extra argument, so there were two type arguments, and we'd only supplied one here.
What example?
I'm trying to think of a polymorph that's like A, we for A to B to B or something.
Okay.
But I only give it two type arguments, but only
Okay.
one value argument, so I know.
Type, and we'll make them in square brackets for all. B,
Or A doesn't matter.
yeah. F equals lambda A, V. Oh, no, we can't do that. We need A to A, something like that. X dot X, right? Right. And maybe we don't even know we're in a context where we have that. We don't even know what F is, right? And you're saying, right, or something, and then we say, is G F A1, A2, X equal to G F A3, A4, Y. Right? In fact, maybe to type check it, we'll make that both X. Right? X has type A1. Right? Something like that. Are these equal to each other?
So here's the B doesn't appear at all, but supposing F actually has A to B to B or something.
A to A to B to B. Yeah, but in that case, that's a little bit hard.
Application to that, right?
Yeah, yeah.
So never mind the G applied to. Is F applied to A1, A2X equal to F of A1, A4X?
This. Yeah. So here we can't even,
So now the type of that whole thing is A2 to A2 on one side and A4 to A4.
yeah, so we can't even say that.
Oh,
Right? Equality requires the types to be the same on both sides.
I thought we had heterogeneous equality.
Well, we would have to define heterogeneous equality, right? We could define it, just like Koch defines J-amique. We can define it. But here, we're using a homogeneous equality, right? So we can't even say it when they're going to be the same. Yeah, I know. I had the very same reaction the first time I heard about it, right? When Bruno Bernardo was explaining this to me, I'm like, you can't just erase those types. They're not important. But the more I thought about it, the more I realize that actually maybe you can. Because when you think about it, so type checking is deciding when two expressions are equal to each other. What does equality mean? Where does equality come from, right? It comes from your semantics, right? You have to have a semantics of expressions to just be able to define an equality, right? It means two things are equal if they have equal semantics, right? And what is our semantics? Our semantics says that you can erase things, right? So if our semantics says you can erase things, why shouldn't our equality allow you to erase things, right? And now you can't erase things that are relevant. Like you can't erase int in list int, but that's part of the type. But when it's just the type argument to a polymorphic function like ID, that's not semantically relevant. And so it's not necessary for the equality. So this is fascinating stuff. I haven't really talked very much about how we implement these for all constructors, but I will just say two words about that and end there. So checking whether a function that says its argument is an erased argument is a lot like just checking a normal function. We just have an extra condition. We have to check whether we have to make sure that argument wasn't used in the body of the function. So this is our same code for type checking lambda expressions, but down here we have a few extra lines, right, that says that when we've marked this as an erasable argument, we better make sure that it actually is erasable, that it doesn't appear in any important positions. And then I define these important positions just following how ICC star does. I define the important positions by defining an erasure function that only keeps around the important information. So if it was in a type annotation, it would get erased. Or if we used it as a proof for subst, it would get erased. Or we use it as a proof for contradiction, it would get erased. Or if we used it as an argument, an implicit argument, or an erased argument, it would get erased. But everything else stays. And so if we actually use it, then it's going to show up as a free variable in that erased term, and then we'd get the error message. But if it only appears in those annotations, in those irrelevant parts of the term, then all the uses are going to get erased, and this check will succeed. Right? So it's a pretty slick trick to kind of figure out when something is allowed to be an erased argument. Okay, so that's it.
The same for equality. When you're doing equality,
Huh?
just erase first,
Yeah.
check for equality, and then
Yeah.
you have to duplicate the information about it.
Yeah. So I haven't done that in this implementation, but we could rewrite the implementation so that it erases first. Yes. Yeah. Okay. At this point, we've gone through pretty much everything in this code. So I've given you this this sort of sample implementation of this dependently typed language. It has a lot of stuff that we talked about, but it has a lot of stuff that we haven't talked about. And so I strongly encourage you to listen to what Simon says about type inference later today. Think about how you might incorporate type inference into this. It's still pretty, if you look at some of the example files that are distributed with it, they're still kind of annoying to write, because there's a lot of things that the compiler could figure out for you if it were just a little bit smarter, if you threw a little bit of unification at it to try to figure out what some of these arguments are. Right? So you could think about how you might extend it with unification. I didn't say anything about co-induction. I didn't say anything about non-termination. Those are a lot of open problems. I didn't say anything about like adding type classes to this, which would be a really or some other sort of constraint mechanism. So what I really encourage you to do is go to GitHub, get your own copy of it, make your own branch, play with it. Try to have some fun with it. Play with what's there, write some code with what's there, get really frustrated with that code, and try to make it better. I'm sure you can. I'm sure there's going to be bugs in it. Fix the bugs, tell me about it, but make your own version. Okay, that's it. That's all I have for you. I hope you have some fun with it.